So welcome back. Glad you are still surviving here. And we will change the subject a bit. You heard about the exhibition, and you have to go and see it at one stage. You know that. And but it is at the Art and Science Museum. So Singapore has had this wonderful idea of having an art and science museums. You put them together. And because this was something that was very dear to Richard Feynman. As we heard a lot, on Saturday, he was very interested in, he was sketching, he was drawing, and he was playing bongo drums, and he was using other parts of brain also. And so it's very appropriate that in this session, we're going to concentrate on Feynman and art. And in order to have someone lead that, we need someone who is both a scientist and an artist. And they should be accomplished in both. And they're not so easy to find. But Robbert Dijkgraaf not only is the director of the Institute for Advanced Study at Princeton, he's also an accomplished artist, has drawn very many beautiful posters for string conferences, and they are extremely valuable. So if you should collect them. I shouldn't say more. I give the word to you.
Okay. Thank you. Well, it's a great pleasure to talk about this kind of grand topic here. Now, some of you have been on the Saturday, wonderful day at the museum, where I was also speaking briefly. So some of the slides you might see again, but of course we have an opportunity to talk to a broader audience. And I actually particularly want to direct my words to the students here, because I think this kind of interface of art and science is also very much about what it means to be a research scientist, and how to kind of develop your curiosity and imagination, and how to explore. So I think in some sense, Feynman himself would probably be quite, well, delighted, but also a bit embarrassed that his artwork is actually in an honors museum, but then he would be relieved that it's an art science museum. So it's something that's a good thing. One quote that I found, sometime read, I think actually it's from Kurt Callan, is that he described Feynman's art at least as good as Rembrandt's physics. And when I read that quote, I think, it's a pass to do anything you want. If any of you want to explore any other areas, I think you can always say, if you're a musician, you want to play some music, you can say, well, my piano playing is better than Mozart's physics, and you'll be fine. Now, actually, Feynman himself also wrote about his art interest. I like this one here, where he wanted to learn to draw for a reason that I kept to myself. I wanted to convey an emotion that I have about the beauty of the world. It's an appreciation of the mathematical beauty of nature, of how she works inside. A realization that the phenomena we seek result from the complexity of the inner workings between atoms, a feeling of how dramatic and wonderful it is. This is feeling of awe, of scientific awe, like, in the old days, I would say artists would describe as the sublime, that we are part of something much bigger, called the universe, of the universe of thinking, which he felt should be communicated through a drawing to someone who also had this emotion. So I think that's also something we have heard a lot about. Physics is not devoid of emotion. We are very passionate in what we do. And that passion actually kind of very much connects to, I would say, the artistic side of our scientific endeavor. So he was somehow able to combine these these worlds, the world of art and the world of science. And now, just a little personal anecdote. For me, actually, I studied physics, in some sense, as my thesis advisor here at Hoofd describes it. Robert studied physics, got bored, went to art school, got even more bored, went back into physics. So it seems like a very roundabout way, but I often felt actually that kind of zigzag movement was actually for me the shortest path to be a researcher. Because one of the great things you learn in art school is not so much about getting a perfect score. There's no such thing as a perfect drawing. It's more about how do you dare to explore and how free you are to kind of make things your own. The moment you put a pencil on paper, you're basically already making something that's completely new and original. So there's this kind of vast space that we are exploring, the space that Frank kind of beautifully described in the previous lecture, this kind of great unknown of everything you can make and study, etc. And so we are a little bit kind of anxious to explore that large territory. And I think the artist inside all of us helps us exploring this. Now, I must say, when I was in art school, at some point I had to tell them that I went back into physics, and there was a lot of information in that sentence because I'd never told I had a physics background. My greatest fear was to be the best artist among physicists, or the best physicist among artists, and thank you for introducing me like that, Lars. So when I said I went back into science, the director of the art school said, "Oh, I know the perfect job for you," which is technical drawing. And I had this image of these two lofty mountains, and there's this swamp in between where you don't want to end up. But then actually all of us, or if we are making our PowerPoint presentation, we are doing exactly that. So I guess like Firemen diagrams are somewhere there, right? They're in that swamp, and so perhaps it's a very pleasurable place to live. I also think there's a long history. Many people say they reminiscent, so to say. Well, wouldn't it be wonderful if we lived in the 18th or 19th century, where scholars and scientists and artists were all unified in one person. We didn't have that division of labor. We had people, in some sense, who were doing everything at the same time. But I must say, sometimes if you read about that time, I would say that's not the way we want to go. So in that time, it was quite common, I know in the early 19th century, if there was a scientific lecture, your colleague would stand up and actually improvise a poem describing you. Artists were actually doing these very kind of academic drawings, which are like anatomically correct. So I would say that was a time where perhaps there was a lot of interface, but it was more of the shiny outside of art, and so the scientific elements of art, so to say, and the artistic elements of science. I think actually these days it's much more interesting, because if there's any contact, it's much more, I guess, as Feynman really exemplified, about the vulnerable insight, both of the research process as an artist or a scientist. Now, we all, in some sense, we're already breaking protocol by giving PowerPoint presentations here. We should actually all use the blackboard. It's the favorite tool of theoretical physicists. And I have my own theory why we love blackboard so much. Instead of any other way of communicating. I think actually it's the reason why is that blackboards are so easy to clean. So you can write something on the blackboard and wipe it out very. The worst thing with whiteboards is that you use the wrong marker. You write something permanent, but it was just a thought. So I also want to talk about mathematics, because I think mathematical beauty is in some sense very much, I think, part of the aesthetics that Feynman explored. So there's this wonderful quote here where he says, basically tells you if you want to study nature, you have to study the language that she speaks, and you have to learn mathematics in order to capture the real essence of what the beauty of nature is. I think many of us feel, if you wonder what an electron is, in the very end, it's a solution to the Dirac equation or something. It's very difficult to have any other image. In some sense, that is the most powerful image, and it's terrific that in some sense this very brief equation can completely capture the essence of this elementary particle. I think we find our mathematical formulas beautiful, almost like the joke, it's somehow impact per symbol that kind of captures the beauty of these mathematical symbols. I showed this already on Saturday, but it's also this other quote, which very much captures the essence of theoretical physicists, that they're extremely arrogant. If all mathematics disappeared today, physics would be set back exactly 1 week. That is to say, if we just together, we would just reconstruct all of mathematics if we needed it. And this kind of famous answer, actually it was Michael Atiyah who gave that answer. That was the week that God created the world. I love that quote. But here's a more serious quote. This is Galileo. writing in the 17th century. Philosophy is written in its grand book, I mean the universe, which stands open to our gaze. It's written in the language of mathematics, which in his days was particular, Euclidean geometry, so triangles, circles, and other geometrical figures, without which it's humanly impossible to understand a single word of it. And without these, one is wandering around in a dark labyrinth, which is a beautiful image. Since that without our mathematical knowledge, we would be just feeling our ways. Now, Feynman had a very complicated relationship with mathematics. This is heard this morning. He was both very dismissive of it, and then one of the star students in mathematics. Great that he was in the Putnam team. And there's this wonderful exchange between him and Wheeler. Wheeler will resurface later again, where Wheeler had this ambitious program in the 1960s to get physicists and mathematicians together. This was part of the invitation letter. Talk about intuitions and motivations and examples. So how do mathematicians think? How do physicists think? And Feynman's answer was very simple. I'm not interested in what today's mathematicians find interesting. Which in many ways, I think, understandable. Because, mathematics and physics and something diverged very much in the 1930s, 50s, where mathematicians actually hadn't really done a proper job of, having a clear logical basis of their mathematical structures, and felt that they had to go inwards and reconstruct mathematics in a very abstract and conceptual way, some sense very far away from the practical approach that Feynman, at least externally, tried to project. So I don't think that somehow does capture in many ways the thinking in the 1960s. Now, there are various points of view where the role of mathematical beauty in physics. The most extreme case was already mentioned earlier, Dirac, who has said it's more important for equations to be beautiful than to have them fit experiments. Not quite clear what he means by that, but I guess there's a certain sense in which the right mathematical equations can be kind of smarter almost than the person who has discovered them, in the sense they have a life of their own. But I also like this quote from Wheeler again, that says, every law of physics pushed to the extreme will be found to be statistical and approximate, not mathematically perfect and precise. Which is a very powerful principle, and the great thing of this principle is that it actually allows for new mathematical ideas to come in. If it's only an approximate beauty, then there's always a way in which it can even be more beautiful. So a good example, again, of the kind of perhaps the wrong applications of this feeling is Kepler. So, I want to briefly introduce that example again. So, like to joke, this is Plato's standard model of elementary particles. In the Greeks, you had the 5 Platonic solids, you had the 4 elements, and there was this kind of correspondence where at least 4 of the Platonic solids had a natural fit with the elements, somehow entirely based on their shape, like water had to roll, so it must have been the icosahedron, which is the most rounded of the 5 solids, and then the universe was, so there was one solid left, which was the dodecahedron, and that was the quintessence, the 5th element, and supposedly be the material out of which everything outside planet Earth was made of. And if you go through the history of art, you will see many of these dodecahedron. Just a few. I'm also putting this wonderful piece of Jung Ong that we saw on Saturday. Leonardo, of course, all of them. In fact, it's interesting that, so this is a very cosmic symbol. One of my favorite dodecahedra are actually in what's the old Parliament Hall in the Netherlands. So they're hanging here, 2 of them. They're light ornaments, and so they were criticized by one of the Dutch politicians. He said, he found it such a wrong statement to have 2 soccer balls hanging in this. Not realizing, in some sense, what the long tradition of that kind of mathematical art was in history. As I briefly mentioned, I think Saturday too, I thought it was a dodecahedron, but this is it's a very long theme. So this is wonderful clay tablet that was almost 4,000 years old. It actually doesn't describe a dodecahedron, it's an icosahedron, but actually describes how to build one several meters high, made out of copper plates. So it's kind of important I find it fascinating to realize that 4,000 years ago, there was an artist or an engineer or a scientist that was in some sense producing this kind of same mathematical object. And of course, we can only speculate why and how. So Kepler was clearly much in love of these Platonic solids, and his famous, this is often seen as a famous example of the wrong application of mathematics, mathematical beauty to nature, is this kind of cosmology, where he put the 6 planets at that time, the concentric circles around the sun, and so there are 5 numbers, which are the relative sizes of these radii of the circles. And by experimenting with the 120 ways in which these 5 solids can be put into each other, he found one which was pretty close. And that was his kind of first cosmology. Of course, it's no longer, there are many reasons why this is wrong, but I love the fact that it is wrong because Kepler himself found that it was wrong. So he found that he was, of course, famous by his first law that says that planets are not moving on circles, they're moving on ellipses. And again, this was a tremendous point of somehow one moment in the history of science where nature really became much more ugly. He writes in his diary that he feels that he has to put a horse cart of manure inside science because he takes the perfect circle. And before that, all the motions outside planet Earth were supposed to be perfect, and the circle is the perfect shape. So to have an ellipse is kind of a very ugly object. But then actually in that diary, then he also writes that he had to bring this horse cart of manure in order to bring again order of a different kind of magnitude. And of course now we know that all these objects are conic, so there's a kind of a nice universal picture behind all these solids. Now, I think that's another interesting element in the way in which beauty guides us through science, is that it's an evolving subject. So here's Feynman describing this. It's not necessarily, you might be in a situation where you have a beautiful theory, and then there is an ugly experimental fact that, at the first time makes you a little bit uneasy, and at some point destroys the whole mathematical order. That in some sense what you thought was a beautiful theory is actually a big mess. And then, time and again, we have this moment where again a new sense of beauty emerges. But we shouldn't forget the losses that we take when we go from one transition to the other. Now, I guess when Planck introduced quantum mechanics, he said literally, I think, that he was able to make any sacrifice to make science survive. And of course, there were huge sacrifices in building quantum mechanics. We gave up the deterministic system, we gave up a nice visualization of what's happening around us. So in some sense, I think it's more like moving in this kind of mountain landscape. Now, there are various places, kind of meadows, which are beautiful and nice, but then somehow we have to move on. And it's the remarkable thing, I think, great scientists are somehow able to have kind of tunnel vision and see through the barriers around us to kind of a new place where, in a sense, again, beauty and order exist. Now, it's kind of quite an interesting philosophical question. What makes us like certain scientific concepts more than others? I want to bring to your attention a discussion actually that was started by a great mathematician, Bill Thurston, unfortunately passed away quite a young age. Great geometer, the person who basically developed all of three-dimensional geometry. And he wrote a terrific article on proof and progress in mathematics, where he discusses what's essentially what would be the best definition of a mathematical subject. And he gives an example, the derivative. That's something that we use all the time. So how do we think of a derivative of a function, say? And then he starts to give the definition. So the first definition he gives is the thing that's there, which the mathematical you get in your calculus courses, epsilon delta. It's quite remarkable if you read the paper, he actually gives it the wrong formula. So he didn't even check it, I think. He interchanged the epsilon and delta in some way. Okay, that's one way to understand it. But there are many others. For instance, we come with a very natural intuition of velocity. even children understand velocity. And if you have the concept of velocity, of instantaneous velocity, you also immediately understand that you can take the derivative of something which has more than one variables. Could be a vector, could be in a higher dimensional object. A velocity can have a certain direction. Then there's the idea of a slope. So if you understand the slope, you could take the derivative of a function of more than one variable, for instance, of two variables. You can think of it as an infinitesimal. Of course, that's how it was born in the 17th century through Newton and Leibniz. So take very small changes and see the effect of very small change. In fact, you can think of it as starting with a discrete function first that jumps and have that. It's an incredibly important concept to have in your mind too. Otherwise, you would never able to kind of program a computer to solve a differential equation. You can think it in a symbolic way. And if you understand it in that way, you can differentiate things which are completely different than functions. Then he says you can make it linear approximation. You can think of it microscopic, zooming in a certain structure. All of these concepts are very useful concepts. And then at some point he goes on, and there's like definition 37, which I'm not quoting. It says, he needed that definition at some point of the derivative to prove an important theorem. But I guess his point is that in some sense, a great physical concept, a great mathematical concept, has all these different facets coming together. And there might be not one unique point of view. And so it's in some sense this multifacety that actually I think is part of it. Also, I think, even if I would just kind of do a little poll here in the audience to see, what kind of mathematics do you find beautiful? There are basically two kind of tastes too. Some people like general structures like vector spaces and equations, etc. Others like very exceptional things. They like the dodecahedron. There's only one that exists. There's something the most beautiful. Well, I guess there's also a much more general principle. I also want to say something about the birth of Feynman diagrams, and I covered this on Saturday. So the first thing is to think about space-time. So space-time, I always kind of visualize, if you have a movie, you can take images and stack the images on top of each other, and you get these kind of paths. So the fact that particles are in some sense path world lines through space-time was an incredible useful theme. And it's this Pierre mentioned this morning again, this great conversation between John Wheeler and Feynman about why, in some sense, and I think that's something that's an incredibly deep fact, that elementary particles are quantized. So there are excitations of a field, and therefore they all have the same properties, charge and mass. Wheeler had this kind of great idea of the single electron in the universe. So let me show it again. So this is electron. It's supposed to go both up and down. That was Wheeler's image. And if you cut that knot at various places, you would have one electron if you have a single strand. But if you cut it in the middle, you have many electrons and positrons. And famously, Feynman said, this is actually not the way the world works, because there would be equal number of positive and negative charges. But actually, I think this is incredibly powerful images to understand, in some sense, renormalization. So the fact that the electric charge is different at various length scales, actually this image is a very good image to use, because in some sense it's exactly, you can think of it as the zigzag lines of an electron. And if you kind of zoom in the path of an electron, you see kind of more of this structure, and that actually is a cloud of electrons and positrons surrounding the core electron. So I think, again, an incredibly powerful visual image to understand this process of renormalization. So this is a picture of Feynman's notebook, where he's for the first time actually exploring these paths. I like the fact he's sending the electron, with straight edges, go back in time and up in time again, and sees how the various components add and subtract and cancel out in a nice way. And of course, this led to the famous diagrams that are everywhere. I always like to show this picture. It's the standard model as written down by Veldman. just to kind of point out that it's not elegant and it's not beautiful. But I think it basically tells us that any beautiful mathematical equation, if you write it in components and use bad notation, it looks very ugly. So I think he wanted to make a point here that it might be beautifully mathematical, but it's incredibly rich and a complicated theory. And then again, we got the famous Feynman diagrams. I love the fact that this morning we heard about the dangerous Feynman diagram. Here's the van again, with Michel in the picture. It was said that there is no diagram that looks like Feynman, but I just pointed out to John that actually in the exhibition there, if you look careful, there was this Feynman diagram, which actually I think looks like Feynman. It has many disconnected components, but I love that piece of art actually. So the reason I think why this kind of drawing and making pictures was so important, that if you think about it, the development, both in math and physics, and applications of quantum field theory, how important was it to have these visualizations of diagrams. So for instance, to give one example, in modern knot theory is completely based on almost this kind of Wheeler picture in a very literal way. Of course, not now thinking of particles, not as moving in four-dimensional space-time, but in three-dimensional space-time, so two space dimensions and one time dimension. If you have a particle that is a quantum particle, it could have this very complicated vacuum diagram. It could have very many kind of knotted figures, and you can calculate them. So there is a very modern knot theory uses this concept in a very powerful way. So you can think of a knot as a trajectory of a particle that is allowed to go both up and down in space-time. In this case, would be Euclidean space-time, so actual three-dimensional Euclidean space. And then the rules of quantum field theory would allow you to, this would be a very simple diagram, but you can have more complicated diagrams, where you think of this as a quark and there are gluons that are exchanged, and this will build a complicated diagram, and actually you can compute this. And actually this incredible, powerful tool, modern tool, that mathematicians use to classify, in this case, knots, but it's actually been applied to many other realms of topology. So the very visual way in which we think now, thanks to Feynman, about quantum processes is actually extremely useful in mathematics. Of course, string theory itself, we wouldn't be able to draw string theory world sheets if Feynman diagrams haven't been there. It's a very natural next step of generalization. Instead of going from diagrams, going to two-dimensional surfaces. Where in some sense, it's a very natural way to include topology. In fact, modern quantum geometry, so to say, is, again, this is this kind of space-time foam picture. If you can have space-time itself can be kind of a Feynman diagram. It can fluctuate. So it's a very visual way of understanding our geometry. Now, as I said, we want to go back to this idea of combining art and science. And I would say, in some sense, in mathematical terms too, this is very much connected to two fundamental ways to understand mathematical structures, which are kind of geometry and algebra. There's sometimes being said, geometry, of course, is kind of moving in space. It's very much connected to the right side of our brain, where we can visualize things, we can walk around something, you can look at things from various angles. And there's the algebraic approach, which is much more using time. Now, if you have an algebraic argument, if you have an algorithm, you do this step by step. I noticed that, in many ways, there are people are almost, biased in one of these two ways of thinking. If you want to give somebody directions, for some people it's very nice to know it as an algorithm, go left, go straight, go right. Somebody like me would love to see a visual diagram, because then I can find my way. And in physics, in fact, we have a similar kind of two opposites. Clearly, general relativity is a geometrical theory, while quantum mechanics is very much an algebraic approach of view, much more using words, so to say, or algorithms, or algebra, instead of geometry. Now, this kind of these two approaches also very much linked to where we kind of see mathematical beauty. So there's this kind of distinction to kind of bad, the ugly things and beautiful things in physics. And I would say if you're a particle physicist, you would typically argue that, the big mess is the thing that you see around you, and the beauty is if you go to the smaller structures. So if you just reduce, we hope that, if the elementary building blocks exemplify beautiful mathematical formulas, like Yang-Mills or others, the Dirac equation. That's one point of view, where in some sense, the greatest beauty is found at the bottom, at the smaller structures. Now, there's a completely opposite point of view that, take for instance any material. You can think of, say, water, as in this bottle. You can think of it as being made out of many, many molecules. It's completely impossible to describe the complexity of the behavior of these molecules. But we know that out of it comes something very, very beautiful. So actually I would say in this, I've interchanged garbage and beauty here. I guess that's my particle physicist bias here. Beauty is given at the largest structures. In fact, this is very much kind of the beauty that Wheeler was advocating for. It's something that, in some sense, it's the laws of thermodynamics are very beautiful. They never ever realized, because they only realized in the strict mathematical limit of an infinite number of particles. But it's a very robust kind of beauty, because it doesn't really matter so much what the constituents are. That describes the intimate structure of matter. It's this grand structure that appears at very large scales. So I guess one important message that we learned in theoretical physics is that we have these two principles of reduction and emergence, and we have these various kind of layers in our cake, where in science various structures appear, whether it's like biology or chemistry or physics, nuclear physics, particle physics, etc. And there are these kind of two arrows that allow us to kind of go left and right in terms of length scales. Now, again, also in mathematics, there's, or I would say in physics too, there's in some sense, what's more fundamental or not. So typically, in mathematical terms, I would say there are two ways, in some sense, to go between geometry and algebra. The traditional way in which we do it in theoretical physics is to take a geometrical object, like, for instance, the knot that I just showed you, and compute something with it. So take a geometrical object and bring it into the world of algebra. So make something very abstract out of something very concrete. The remarkable thing is that just the last few decades we've seen there's something like the opposite. So in this point of view, it's kind of a reductionist point of view, and in the end, it's the abstract algebra that would take over, and the role of images or figures or geometrical structures is, in some sense, only kind of a starting point. There's a very opposite point of view, where, in some sense, geometry itself can emerge. So it's no longer fundamental. It's something that kind of appears out of algebraic structures. And I think this is a very deep theme in modern theoretical physics. That in some sense, you can have both an arrow going one way and go the other way. And in some sense, the two belong together. And I think that's where deep intuition these days from string theory and quantum geometry is coming. It's kind of bringing these images very much together. So I won't have time here to explain this, but in modern quantum geometry, we have theories that are entirely living in the world of quantum mechanics. There's no such thing as gravity or general relativity or anything. There are theories which are truly gravitational theories, and they are somehow equivalent. So there are 2 points of view on the same physical system, one using geometry and one not. And you can think that the geometry or general relativity is emerging out of this kind of quantum system. Now, in some sense, I think in these models, it looks like that space-time itself and geometry itself, and even the motion of particles in that geometry, is all emerging out of something much more fundamental or equivalent, which is quantum information. Now, I want to kind of go along a little bit on this theme. I'm the theme is of looking at the world from different perspectives. There was a question here, what is the most promising field in theoretical physics? But one thing I think which is very kind of somehow characteristic for the times that we're living is that we have all these different kind of areas in theoretical physics, and they seem to a large extent to overlap. So the way I see this is that this is a time where we are building a lot of dictionaries between various kind of approaches to physics that are trying to capture one and the same thing, but in a kind of in a different language. So it's a little bit like speaking various languages to capture the world, and then just as in languages, some words are very difficult to translate to the other language, and vice versa. And I think if you're a modern, young physicist now, the good thing is to be multilingual. Try to kind of learn at least two of these languages, because you will be in terrific position to take ideas from one into the other. So I think Feynman, as no other, was able to kind of capture or have this ability to see many things at the same time. So I think that we already heard this morning about this kind of invention of the path integral. We'll learn more about it in the subsequent days. But the great thing I like that, he was pointed, Dirac said that there was an analogy essentially between the two, and Feynman describes this, I think, in his Nobel lectures. What does Dirac means with analogous, and then he realizes, wait a moment, he means equal, which is a terrific insight, So what do you mean, how to go from A to B? It's actually an equal sign that connects the two. And of course was an incredible powerful thing, because now the Hamiltonian and the Lagrangian formulation of quantum mechanics, since they were equal, you could do calculations on both sides. And we all know there are cases where the left-hand side or the right-hand side is a more effective way or easy way to compute, or actually gives more insight. So I would like to point out, it's kind of my mission, in some sense, that, to speak on behalf of the most ignored mathematical symbol, which is the equal sign. So actually, philosophers have long debates about this, about what exactly the equal sign means. And I learned that they call this Clinton's principle, because he had this saying at some point was the meaning of is. It's a long history, we won't go back into this. But if you think about it, now the equal sign is incredibly subtle. But even if you say, right, 1 + 1 = 2, you don't really mean that they're exactly the same. On one hand side, you take two numbers and add them. So whenever you write an equation with an equal sign, you're doing something quite remarkable. You're equating two things which on the surface are not equal. You're making a very powerful statement. And I love to think that, it's the image I have is sometimes you have continents and they kind of bump into each other, and then certainly there are animals living on both, and then they can cross from one continent to the other. And the same thing is with the right kind of mathematical formulas. That it's very appropriate. The equal signs are two lines, because you can both move from the left to the right and the right to the left, and ideas can switch. Now, if you look at famous equations in physics, you will all have, I think, that property. For instance, this is Planck equation that launched quantum mechanics. I put them on T-shirts because I feel every good equation should be put on a T-shirt. The energy and the frequency of light, why would they be connected? That's, it's terrific. He needed to have a new symbol, so to say, to do this. These two worlds were not able to communicate before that. Equals mc², energy and mass. Why would they be together? The fact that the most amazing thing is if you would know anything about that equation, if you would tell a physicist at that time, well, I write one equation somehow connecting the two, that already would be incredibly stimulating thought. General relativity, the equation is a little bit more complicated, but still fits. Could even add the cosmological constant. Slightly smaller font, it would still be nice on a T-shirt. The left-hand side is something, it's a Riemannian geometry, belongs to the world of mathematicians, curvature, etc. The right-hand side is about energy and mass and movement. The fact that these two actually can appear on one line is incredible, complicated, and remarkable. Heisenberg's principle I would like to write it like this, it's not basically using the Schrödinger formulation. The fact that you have momentum and position in some sense, connected together. The duality, the particle-wave duality, again, is a terrific example. It's another example where there is an equal sign, and there's a way to go from the left to the right. We call it Fourier transform. So you can use one set of variables, the other set variables. And we can connect them in a very powerful way. I mentioned this on Saturday. I want to mention once again, there's this, when Heisenberg finds his formulation of quantum mechanics, he writes to his friend Wolfgang Pauli, and Pauli writes back this postcard. This is exactly what Pauli says. He says, I can see the world with the PI, and one can see it with the QI, but if one opens both eyes, then one becomes crazy, which I think is the most wonderful description of quantum mechanics that I know. So there's this remarkable fact that, you can, with one eye, you can see the momentum interpretation, the other one you can see the wave interpretation. It's very difficult to open both eyes. But I think we should, And I guess my point I want to make is that, Feynman was one person that really could open both eyes. In fact, it's kind of a nice, almost metaphor, but it's also a true story. So just want to mention a person who was really able to combine science and art in a very powerful way was Ernst Haeckel. You'll perhaps know these wonderful pictures he made of microscopic animals and other creatures. So he was trained as a medical doctor, basically failed. Then he wanted to become an artist. He went to Italy, again failed. And at some point he didn't know what to do. And he saw people, was reading some scientific articles, and there were a lot of naturalists. And then he asked a local fisherman whether he could just, look at some of the fish, and was not very, he had to do something original. And then he noticed these very tiny animals. And he had the ability, which turns out a key ability for him, that he could look with one eye through the microscope and with the other eye to the page and draw. And that's very difficult to do at the same time. So he had this ability to literally see art and science, open both eyes. It's a great metaphor, and able to somehow combine the two different perspectives. So I think this theme of having many different perspectives, art and science, or the various components in our understanding of the physical world, is, I think, quite important. I think it's very connected to this kind of Gestalt theory in psychology, that you can take a certain image and you can see several interpretations of that image. Of course, Niels Bohr was very fond of that idea. Now he developed it perhaps to a certain stage where it became less scientific, but still, believe very much so. He had this sense of complementarity, that everything should be, there should be two complementary points of view of everything. And one of his famous was truth and clarity, which I guess, what we would say now, it's either mathematical rigor or physical intuition. So, if you, we heard this morning the quote of Feynman that if you're too rigorous, you don't make progress. So we could have a separate debate, whether the kind of mathematical beauty is really necessary, or we need some approximation so that we can save, so to say, our physical intuition. But it's, I think it's very important that I think that's one of the lessons I learned from Feynman and his kind of spirit. It's important to have the ability to at least switch through these various perspectives. And on the end, to say one word about another amazing ability he had, but he had this very strong case of synesthesia. So synesthesia is now a phenomenon that's very much studied by psychologists. It's the idea that you basically confuse the senses. So the most simple form of synesthesia is if you see a letter, that letter corresponds to a certain color. I have it myself, but I noticed if you talk to other synesthesiasts, they often have it with the days of the week or the month of the year, numbers, of course, sometimes, but it could be very different. The most famous case was Nabokov. He had it a very strong way, the writer, and he tells the story when he was like 4-year-old, he gets a little cube, and the cube has letters on it, and they have colors. And then he says to his mother, the colors are wrong. And she immediately understands what's going on because she has synesthesia too. In fact, I think he gives an example where his mother, I think, sees the letter, I don't know, M, blue, and his father sees it as red, and he sees it as purple. So the colors have mixed. It's a wonderful property, and it's for instance, for me, it's very helpful. These are the ways I see numbers. I see them in color. Very easy if you want to remember a telephone number. And here's Feynman describing it. Now he tells us that he sees his equations in full color. This is the Bessel function: light tan J's, slightly violet bluish N's, and dark brown X's flying around. Now this is perhaps a bit disorienting if you don't have synesthesia. It's even worse if you have synesthesia, because for me, clearly, the J is blue, the N is green. So I actually remember when I was learning history in school, I would look at the map, the world, these historical maps, together with my father, who had it too, and I would say, I picked this one because actually England and France have exactly the colors that they have. In my mind, he was saying, no, they're totally wrong. So that's a very unpractical language to speak, so to say, if you meet another synesthesiast. But there's one remarkable thing I want to point out, and it's just a little thing to kind of perhaps ease us into the discussion, is that there's something quite remarkable that sometimes you can see colors that do not exist. I actually have this for, if I look at the letter A. The letter A for me is both red and blue at the same time. And this is, again, a well-known phenomena in psychological research. And I read an article about it. It was called Colors from Mars. So some people see both red and green at the same time if they look at something. And so this actually shows us that our mind is able of seeing things that do not exist, in some sense, and we can have somehow a linear superposition of colors or senses. And I think if anything comes close to this saying of Pauli, that you should try to look at the world with both eyes without becoming crazy, I think it's Richard Feynman. So thank you very much.